Alright, in this video we're going to take a look at the period for the graph of sine and cosine. So the graphs of sine and cosine functions are periodic in that the pattern is going to repeat itself infinitely in both directions. So here we have a graph of cosine of x in blue, and notice it's the same graph to the left of the y-axis as well. And as a matter of fact, we take a look at the graph of cosine of x. If we zoom out, notice it just has this wave-like pattern forever going to the right and also forever going to the left. So, oop, didn't mean to do that. I can just reset the 360 and 60, 360. If you're wondering, that's how you do it. So notice we have forever to the left and forever to the right, that pattern. So the part in the graph in purple or blue is a copy of the other one. So, or in this case, red, I should say. So we're just taking, we copy the graph and we just paste it forever right and we paste it forever left. And that's because the cosine function as well as the sine function is periodic. So each of the following ways are ways in which you can think of the period of the graph of a function. It's how long until the graph starts repeating the same values in the same order. So if we take a look at the, you know what, let me fix this to step of 45. And we'll go y is -3 to 3. There we go. If we trace along the graph, we get 16 degrees, 0.961. We go down to, we get to -1, and then we go back up again. And then once we start back at 1, as we did over here, then we go and trace the same values, the same y values, and they just keep cycling through from 1 to -1 and back again for cosine. Another interpretation is it's the least amount of the graph you need to copy and then paste it before and after. So in other words, here we got a full cosine wave from 0 degrees all the way to 360. We cover going down and then all the ones coming back up. So if we just took this piece of the graph, we could just copy and paste it forever to the right, and we could just copy and paste it forever to the left. So it's the least amount of the graph we would need to copy in order to paste the rest of it. So in this case, 360 degrees. And if the units along the x-axis were length, then the period would be the wavelength from science class. And that's actually the way I interpret the period of graphs, more of a wavelength feature. So if we take a look at the top of 0 degrees, the cosine of 0 degrees is 1. All the way out to 360 degrees, the cosine of 360 degrees is 1. And for sine and cosine, the period of our graph is 360 degrees. It takes 360 degrees or 2 pi radians to make one full sine or cosine wave. So in this case, our period is 360 degrees before we just repeat those same patterns. Or again, you could think of it like wavelength if this were 0 and let's say 360 centimeters or something to that effect. So we can adjust the period for sine and cosine functions by multiplying our input values by a positive number other than 1. So in other words, if we multiply our inputs by a positive number other than 1, that's going to cause either a horizontal stretch or a horizontal compression towards the y-axis for our function, and we'll see that. So the equation for adjusting the period for sine and cosine is sine of bx and cosine of bx, and we're going to take a look at some examples here in a little bit. So example 2, we're going to use a graphing utility such as a graphing calculator to determine the period of each of the following. So we're going to start with the sine of 2x. Sine of 2x. Now before I do the sine of 2x, I'm going to look at the sine of x. So here's our sine of x wave that, just normal y equals sine of x. Notice again, this one from 90 to 450, the period here is 360 degrees. 450 minus 90 is 360 degrees. But if we take a look at the graph of sine of 2x, here's the sine of 2x in blue. And if we pair it up with the original red graph, notice we have we get two of these waves in the blue graph for sine of 2x, two of those sine waves in the time it takes the red sine wave to make only one. And matter of fact, that's exactly what this number will tell you, which we'll talk about a little bit more towards the end of this video. But in terms of the sine of 2x, this one, we have a 45 to 225, and 225 minus 45 is 180 degrees. And we can see from 0 up to positive 1, down to 0 to negative 1. This one needs 180 degrees or pi radians to make one full sine wave. So 180 degrees or pi radians. All right, example B, we have cosine of 3x. So here is cosine of 3x, and notice the larger the value of b, the more of these waves we tend to get. So for cosine of 3x, now going from the maximum to another maximum, we have 0 to 120, that's 120 degrees. In other words, if we look at we get 1, 2, 3 cosine waves in 0 to 360, and again, that's no accident with this 3 in front of x. So for cosine of 3x, our graph said it was 120 degrees. All right, part C, sine of 1/2 x. So let's see what the sine of 1/2 x looks like. Here's the sine of 1/2 x. I'm going to compare that to the sine of x. So it took our red graph and it stretched it out horizontally away from the y-axis. So if you recall back from transforming functions, if we multiply our inputs by a number between 0 and 1, such as a half, it's going to stretch this original graph in red away from the y-axis. So away on the negative side and away on the positive side. But in any event, this one, I'm going to have to zoom out to see this one better. This one has, the top is at 180 and to 900, so that's a difference of 720. 900 minus 180 is 720 degrees for this period. All right, finally, cosine of 1/4 x. So part D is cosine of 1/4 x. This one, we get back to 1. It's going to take us a little bit. We get back up to this value, y value of 1, once we get all the way out to 1,440. So our period for this function for cosine of 1/4 x is 1,440 degrees, or I believe that's about 8 pi radians. So as we've seen, the value that we're multiplying our inputs by, like a half or a quarter or 2 or 3, that value of b has an impact on what the period of the graph is. So with y equals sine of bx and y equals cosine of bx, if we look at those graphs, it seems that the different values of b are going to affect the graph in different ways. So if b is between 0 and 1, it is going to be a horizontal stretch away from the y-axis, like example C and D were. And if b is bigger than 1, it's going to be a horizontal compression towards the y-axis, like examples A and B were. So in each case, our answers for our period is going to be whatever 360 degrees divided by b equals. So for instance, going back to example A, which was y equals sine of 2x, if we take 360 degrees and divide it by 2, we get 180, which is what we said the period was anyway, 225 minus 45. Another way to think about that is one full sine wave, it only needs 180 degrees. So with the 2 that is in front of the x, that means from 0 to 360 we get 1, 2 waves, which means each one of those waves is 180 degrees. So the period for the graph of sine and cosine, if we don't want to actually graph it on graphing utility, all we have to do is take that value of b and divide 360 or 2 pi by it. So 360 divided by 2 is 180. And even when it's a fraction, but keep in mind, with example C, 360 divided by a half, when you divide by a half, that's the same as 360 times 2, which is where we said 720. So from 180 to 900 was 720, which 360 divided by a half equals 360 times 2, or 720 degrees. All right, that about does it for this video, and I will see you next time.